Friends, now we will see the example number 17 of the textbook and what are the given information. That example number 17 of textbook gives us the information that a rocket is fired vertically with a speed of 5 km per second. So initial speed is given 5 km per second from the earth's surface. How far from the earth does the rocket go before returning to the earth? That means we are asked to find out the distance h, that how much maximum distance it will travel with this speed it is fired. So before returning to the earth again, mass of earth is given, that is mass of earth is given 6 into 10 to the power 24 kilogram, and mean radius of earth, that is RE only. So RE is given as 6.4 into 10 to the power 6 meter, and capital G is well known, it is 6.67 into 10 raised to minus 11 SI. So all these things are given. Now from the knowledge we have already obtained that the total energy always remains constant. So what we will do, that total energy of rocket at the surface of earth, total energy at surface, that is equals to kinetic energy plus potential energy, that is kinetic energy plus potential energy. So it is given. Therefore total energy on the surface, that we say total energy is equals to 1/2 mv square, because it is given that it is fired with some velocity. At the same time it has its potential energy, that is Gm me over Re, where small m is the mass of rocket. Now in the same way, suppose at the highest point suppose at highest point its velocity becomes 0, and therefore kinetic energy will be also 0. So say suppose h is the highest point, so total energy at that level, total energy is equals to kinetic energy plus potential energy. But as we know that kinetic energy is 0 and potential energy will be minus G m me upon Re plus h, where h is the highest point that it can achieve. So now we can compare these two total energy equation. So this total energy, that is first equation for the total energy, and this is the second equation for the total energy. We can compare them, we can give them name as equation 1 and equation 2. From equation 1 and 2, when we compare them, we have from equation 1 and 2 what we can have, that is 1 half mv square minus g me m over re is equals to minus g me m over re plus h. Now from this comparison we can cancel out the similar quantity and we can have a new equation, that is 1 half v square minus g me over re is equals to minus g me over re plus h. Now here we are going to apply a new trick. That means what we are going to do is that we are going to convert this equation into the equation of gravitational acceleration of Earth. So to convert these equations into gravitational acceleration, we have to divide and multiply these equations with re square. So for that part, what we will do, here we will keep this 1 half v square as it is. Then in this part of GRE, we send it to the right hand side. So it will be G me over re. Here it will be minus G me over re plus h. Now for the right hand side, we multiply with r square or re square and divide it with re square to convert it into g. So our next step, that is 1 half v square is equals to g me over re square. So here also re square upon re. So we have multiplied and divide. Similarly here minus g me over re square. So here it is re square over re plus h. So here we can see that we have multiplied and divide with re square. So now this portion, this is now our gravitational acceleration on the surface of Earth. So we can have a new term, that is 1 by 2 v square is equals to g into re, because here we will have term of gravitational acceleration, 1 re cancel, minus g re square over re plus h. Here we have to remember that ultimately we have to find out this h. So our main question is to find out the value of this h. That is our main question, and that for that derivation we will move further. Here we will take common terms from the equation. So again here this is v square by 2. Here we are taking g re as a common. So here it will be 1 minus re over re plus h. So from that, if we are taking LCM, it will be g re plus h minus Re over Re plus H. So here after this term we can have that Re plus H upon H here, that is, or I can simplify again, so little bit more simplification. Let's take term that is V square by 2 is equals to GRE H upon RE plus H. Now we will take a simplification for this part. So here we have all other terms except H. So for that part what we can do now, that we will move further, that we take V square Re plus H is equals to 2 GRE into H. Now we simplify this term with our equation. So we can have, that is, RV square, that is Re into V square minus V square, plus V square into H is equals to 2 GRE H. So now we will send this V square H term to the right hand side. So we can have Re V square is equals to 2 GRE H minus V square H, and therefore Re into V square is equals to 2 GRE minus V square into H. Therefore H is equals to Re V square over 2 GRE minus V square, and then we have all the terms which are given in a right hand side bracket. So just put the terms, that is radius of earth or mean radius of earth given, that is 6.4 into 10 to the power 6. Velocity we are given, that is 5 kilometer per second, so 5 into 10 raised to 3 meter and square upon 2, the value of G that we will take as a 9.8, so 9.8 into Re again, that is 6.4 into 10 raised to 6 minus 5 into 10 raised to 3 square. So when we simplify this equation, we have the equation value, that is 1.6 into 10 raised to 6 meter. So that is the height that a rocket can achieve the maximum after projectile from the earth. A question is asked: a satellite orbits the earth at a height of 400 km above the surface. So here H is given of a satellite, that is 400 km, that is 400 into 10 to the power 3 meters. So it is 400 km above the surface. How much energy must be expended to rocket the satellite out of the gravitational influence of earth? Now mass of satellite is given 200 kilogram. So mass of satellite is given 200 kilogram. Mass of earth is as usual, mass of earth is 6.4 into 10 to the power 24 kilogram, and 6.0 here it is given 6.0 into 10 to the power 24 kilogram. Radius of earth is 6.4 into 10 raised to 6 meter. And G as usual in SI 6.67 into 10 raised to minus 11 SI, that is Newton into meter square per kilogram square. Now again we have to find out that energy that we need to do expanded to rocket to the satellite out of the earth's gravitational field. So we need some additional energy. So first of all we have to find out the actual energy. So the total energy of orbiting satellite at height h, we can say that energy at height h we can have, that is equals to minus G me m over re plus h and plus kinetic energy, that is 1/2 mv square. So here also we have one knowledge that v square can be written as G me over re plus h. So we can say that v square is equals to G me over re plus h for the given case, and therefore when we replace it over here we can have the equation that is equals to minus G me m over re plus h, while this is 1/2 m G me over re plus h, and therefore this is ultimately the equation is equals to minus G me m upon 2 re plus h. So this is the equation. Energy expanded to the rocket out the satellite out of the earth gravitational field is equal to minus of this energy. So this is called the binding energy actually, and therefore the needed energy to send the satellite out of the influence of gravitation or influence of earth. We can have the term that is minus of minus G me m over 2 re plus h, and therefore we can simply apply the equation and we can have the calculation that is equals to comes to the answer, that is 5.9 into 10 to the power 9 joules. So this is the total energy that we need to send it out of the gravitational influence. Now we will move to another example. This example, that is example number 20, that is also one of the IMP example of the textbook. So example number 20 of textbook chapter number 8, it is the information given: two stars each of one solar mass. So mass of the star are given, that is 2 into 10 to the power 30 kilogram, that is the mass of sun. So each of one solar mass are approaching each other for a head-on collision. When they are at a distance 10 to the power 9 kilometer, their speeds are negligible. So the distance is given over here, that is 10 raised to 9 kilometer, that is 10 raised to 12 meter. So when they are 10 raised to 9 kilometer apart, their speeds are negligible. What is the speed with which they collide? The radius of each star is 10 raised to 4 kilometer, and assume that the stars to remain undisturbed until they collide, and the G has a capital G has a known value. So here initial potential energy we can have initial potential energy at a distance given above, they have minus G M into M over R. So here the mass is given as a solar mass, we can apply it. Now the total kinetic energy of star that we can have, that kinetic energy for both of them, that will be 1/2 mv square plus 1/2 mv square, and that is total mv square. So that is the another part. Now v is the speed of stars with which they collide. Now when their stars are about to collide, the distance between their centers, that will be r dash, that is 2r. So when they are just about to collide, the distance between the stars will be that r dash is equals to r plus r, that is 2r, and here they have given the radius of each star, that is equals to, that is 10 to the power 6. So here we can have that 2 into 10 raised to 7 is the tentative answer, because each will have 10 raised to 4 kilometer. So it will be 2 into 10 raised to 4 kilometer. So it is 2 into 10 raised to 7 meters. So this r dash is 2 into 10 raised to 7 meters. Here r is given as a 10 raised to 4 kilometer, that is 10 raised to 7 meter. Now from all this given information, now we can simplify the equation, and that is the final potential energy here, that we can have the final potential energy will be minus G M into M over 2R or R dash. So this will be the next equation. Now we can have the kinetic energy is at the cost of loss in potential energy. So the total kinetic energy we can apply now. Therefore here total kinetic energy gain is equals to the total cost of loss in potential energy. So here we can compare both of these equation. That means therefore mv square is equals to minus g m square over r minus g m square over r dash. Now this equation will be positive because minus minus will be plus. Now we can take gm square as a common and we can simplify the term. That will be here, that gm square, if we take the term, it would be 6.67 into 10 raised to minus 11 into that m square is a 4 into 10 raised to 60. So when we try to simplify this part, we can have the equation that is the value 2.668, that is about 2.668, that is 2.668 into 10 raised to, here we can say about that 10 raised to 50, 10 raised to 50 as a unit value. Now we will try to solve this example with putting these terms in above equation. So therefore that mv square is equals to minus 2.668 into 10 raised to 50 divided by r plus 2.668 into 10 raised to 50 divided by r dash. We are having all the values of r and r dash. When we put them, we get this is equals to minus 2.668 into 10 raised to 50 over 10 raised to 12 plus 2.668 into 10 raised to 50 divided by r dash, that is 2 into 10 raised to 7. So it is about that we can have overall value, that is when we simplify this equation we get 1.334 into 10 raised to 43 joule. So now when we simplify this equation, ultimately we have mv square is equals to this value, and now from the equation that v is equals to the square root of 1.334 into 10 raised to 43 divided by the solar mass, that is 2 into 10 raised to 30, and therefore the answer that we need will be is equals to 2.583 into 10 raised to 6 meters per second. Now we will move to the example number 21 of the textbook, that is the illustration exercise example number 21. The information provided in the examples are like this. It is given that two heavy spheres each of mass 100 kilograms. So here we are given the mass of the sphere is 100 kilogram and there are such two spheres are given and the radius 0.10 meter. So the radius is given 0.10 meter of each are placed 1 meter apart. So here radius is given and the distance between them is given. So here we take both of them separately. Here we say the radius of the sphere, that is r, that is radius, and distance between them we take x is 1 meter apart. So on a horizontal table, what is the gravitational field and potential at the midpoint of the line joining the centers of the spheres? Is an object placed at the point in equilibrium? If so, is the equilibrium stable or unstable? So first of all, we are asked multiple questions. In first, that gravitational field at the midpoint of the line joining the centers of the two spheres will be 0. The reason is very clear, that at the center they both are having the same value, but from one part it will be a positive while from the other part it will be negative. So the gravitational field at the center, that will be a 0. Now the potential. So the potential is that we can obtain that potential at center, we can have V is equals to minus Gm over R by 2 plus minus Gm over R by 2. Here R is taken as a x, so we can have the total distance as a x. We can write it as a minus 4 Gm over R, but here R is x as per as our question, or we can take it here as R. So here we can put the equation, that is minus 4 into 6.67 into 10 raised to minus 11. The mass is given as 100 kilogram upon r, that is given 1 meter distance. So it will be minus 2.7 into 10 raised to minus 8 joule per kilogram. So this is the potential at the midpoint. As the effective force on the body placed at a midpoint is 0, so the body is in equilibrium. If the body is displaced a little towards either mass body from its equilibrium position, it will not return back to its initial position of equilibrium. Hence the body is in unstable equilibrium. So here, that is unstable equilibrium is given for it. This is the example 20.